Now we start this new lecture, the 7th lecture on introductory nuclear physics. And I'm going to talk further on binding energy, the stability, and the estimate of radius and density of nucleus, and the force, the nuclear force that is really at the heart of all this. So we are going to discuss further in this lecture. Let's start the presentation. In the last discussion, we have gone through this, that the masses of the individual constituents are calculated, and the mass of the nucleus is then compared, and the difference of the mass is termed as the mass defect, and the binding energy is the mass defect multiplied by c square, or its equivalent 931.5 million electron volts per AMU, and that's how we get the binding energy. And we can divide this by the total number of nucleons to get the binding energy per nucleon. Let's move further to talk about the nuclear stability. And in this regard, it depends on the neutron-proton ratio. How stable is the nucleus will be coming out as a result of the packing fraction of the nucleus, and also the binding energy per unit nucleon. It depends. If we look at the curve, there is a straight line which is shown here, and you can see here the number of protons on the x-axis and the number of neutrons on y-axis. If the number of neutrons and protons are equal, then we get this straight line at 45 degrees. However, the curve really deviates. Initially, it is very close to this, the number of protons and the number of neutrons remain same, but then the gap starts increasing. And this is really desired. Actually, the neutron to proton ratio of an atomic nucleus is should be 1, but in general, it is not the case. The elements that have Z less than 20, that are lighter elements, they have the ratio of 1. So they have the same amount of protons and the neutrons, and they are the stable, and they are the naturally occurring nuclei. So if we compare the forces, the electric repulsive force between the protons, it scales very differently as compared to the strong nuclear force, that is attractive force. So if we want to keep the attractive force dominating, then we have to have more neutrons and less protons. And that's why the stability desires that the number of neutrons must remain larger as compared to the number of protons. And therefore, the gap increases for the large-sized atoms. If they want to be stable, there is ample need that they need to be electrically less repulsive and more attractive. But the attraction is only coming from the nuclear force. So strong nuclear force will improve if the neutron total number is large. nuclear stability depends on this important parameter that the protons in the large nuclei are far enough, then the electrical repulsive force will dominate and the strong nuclear force will be less, and therefore the instability will increase. If the nucleus has to hold, then more number of neutrons will be needed to just give more number of attractive force and to keep the nucleus in a bound form. Thus, N divided by Z ratio will become more than 1 for the heavier nuclei. And you can see this is the real trend for the stable nuclei, that the curve goes up. Let's briefly talk about the packing fraction. It is defined as mass defect per unit nucleon. The value of packing fraction depends upon the manner of packing of the nucleons within the nucleus. And you can see this curve. Let's elaborate briefly. On x-axis, the atomic mass number is shown. The mass number stands for the sum of protons and the neutrons. So atomic mass number is increasing in this direction, and the packing fraction is shown from 0 to the higher values of 0.008 and the lower values minus 0.002. And you can see that the packing fraction is very high initially, and it decreases and becomes very small near the iron, the krypton, and then it goes again high and high and high. You can see the uranium is here. So fission will create the smaller nucleons and will have the packing fraction, small packing fraction. And fusion will create similarly the small values of the packing fraction from high to low, and this will improve the stability. So the packing fraction beyond the mass number 200 becomes positive, and it increases with the increase in the mass number, and that's why the packing fraction creates instability. Lower the packing fraction, the greater is the binding energy per nucleon, and therefore greater is the stability. Mathematically, the isotope mass minus the mass number multiplied by 10 to the power 4 divided by the mass number gives the packing fraction. This is to normalize it to a larger value so that we can read it and explain it, but the packing fraction is the mass defect per nucleon. Here we show the binding energy per nucleon curve as a function of mass number, and it is actually the inverse of a previously shown curve. Here we see that the small binding energies are for neutron, and it increases with the increase in the mass number, and it goes to the large value and becomes very, very large. In between 8 and 9 MeV per nucleon, binding energy becomes very high. Here, closer to the place is the iron and the nickel, and then it starts going down again as the mass number increases. And for uranium and U-238 and the radon, it becomes again small as compared to the iron. The binding energy, larger the binding energy, the stability is very high. And the smaller the value of the binding energy, such a nucleus will be unstable and will tend to become stable. Therefore, we see that the smaller mass number tries to fuse together to become the larger one, which has the more large value of binding energy. More binding energy is more stability, and therefore the fusion is a favored process in the binding energy curve. Similarly, fission is a favored process. Fission occurs and it breaks the large nucleus into smaller 2 or more parts, and they have the binding energy higher as compared to the uranium, and therefore they are more stable as compared to the previous nucleus, and therefore the fission favors the stability due to the binding energy increase. So larger the binding energy per nucleon, the more we see this stability, the more we will come to know that the nucleus becomes a stable one. Binding energy per nucleon, and the important feature of this graph are that the average binding energy per nucleon is about 8 MeV per nucleon. Maximum binding energy per nucleon occurs around mass number A is equal to 50, and it corresponds to more stable nucleus. Iron 56 is located close to the peak with the binding energy, and therefore it is one of the most stable nuclides. Its binding energy is 8.8 MeV per nucleon. The nuclei with very low or very little mass have lesser binding energy, and they become more stable by getting together, and it is easy to separate such nucleus to the constituent nucleons. Fusion energy from binding energy. People ask this question, that how to find out the nuclear fusion energy and how it is explainable with the help of binding energy curve. So the answer is the low mass numbers can go through this nuclear fusion, where the light nuclei are joined together under certain conditions, so that the final product is having great binding energy, and it is greater as compared to the individual participants in the fusion. And the example is deuterium nucleus. It has binding energy of roughly 1.12 MeV per nucleon. Before reaction, the total mass is 4 atomic mass units. So the binding energy for the 2 helium, 2 hydrogens isotope deuterium are 4 multiplied by 1.12 equal to 4.48 MeV. After the reaction, the helium is formed, and it has a binding energy of roughly 7.08 per nucleon. So the total binding energy becomes 28.32 million electron volt. So subtracting the initial binding energy and the final binding energy, we get the 23.84 MeV. So this is the energy which is released in such reactions. And that's how we find out if the fusion is occurring and the D and D are combined to form the helium nucleus, then the binding energy is roughly this. Let's talk about the nuclear structure. How much is the size of the nucleus, and how we can find out? And can we talk about this? The radius of the nucleus is not really well defined. We can't really describe it with a rigid sphere. It has some fuzzy region around it. So rough we can give a radius, but not strictly a radius. For practical definition, the range at which the density of the nucleons inside the nucleus is there. That approximates our model of a sphere, and we can talk about a simple formula for the nuclear radius. It is an empirical formula, and it is given as r equal to r naught, a to the power 1/3, where r naught is 1.12 femtometer, which is 10 to the power minus 15 meters. If we do the scattering experimentation, we can find out that the nuclear density is almost constant. That is, density stands for the mass per unit volume. The density remains constant, and scattering shows this, that the core of the nucleus is rigid, hard, and density is almost same, remains constant and almost same, and the variation occurs at certain distance away from that the nuclear radius in femtometers. So we see that it is constant, it is constant, it is constant, and then the sharp decreases. It is a sharp decrease, but with certain tail, and this tail actually is the cloudy part, the fuzzy part of the nucleus, but the rest of the nucleus is very rigid and very straightforward, forming a good analogy with the sphere, and therefore we can use this empirical relation. Nuclear density is constant. We have seen this r is equal to r naught times a to the power 1/3, and the volume is therefore 4 pi r cube divided by 3, and if we substitute the value, it is 4 pi r naught to the power 3 multiplied by a divided by 3, and that's how we get the volume. Now, density is the mass per unit volume. So mass is A. So A divided by this gives us 1 divided by 4 pi r naught to the power 3 divided by 3. Now r naught is a constant, 4 pi is constant, 3 is constant. Therefore, the whole thing is constant. Therefore, the density is constant. And it is not dependent. The density, that is the mass per unit volume, it becomes independent of A. You don't see any A in this red relation. So we can really show that the density, nuclear density, is constant. It is independent of the mass number A. Let's briefly discuss the nuclear sizes and the shapes. We have seen that the radius can be computed using that empirical relationship. If we want to compute the radius of carbon, we see that the carbon has A equal to 12, Z is equal to 6, and the radius can be 1.2 femtometer multiplied by 12 to the power 1/3, and the answer is 2.7 femtometer, or 2.7 into 10 to the power minus 15 meters. Let us also compute the density of the typical nucleus and find how much mass would be needed if we want to make a nucleus of 1 centimeter radius. If we want a large sized of nucleus of 1 centimeter radius, the density is mass per unit volume, and the mass of the proton is roughly 1.67 into 10 to the power minus 27 kg, divided by 4 pi r naught to the power 3 divided by 3, and this is the volume, mass per unit volume, and we substitute the value of r naught, and we find out the density equal to 2 into 10 to the power minus 17 kg per meter cube. Now, this is the density of the nucleus. Now, hypothetical nucleus, which we would like to have, will have the mass equal to R. I'm sorry, this is not R, this is the density multiplied by the volume. The density multiplied by volume will give the mass. So, density multiplied by volume. The density is given 2.7 into 10 to the power minus 17, and the mass 4 pi into 0.01 cube. This we get from 1 centimeter radius. So in meter, this is 0.01 cube divided by 3. So 1 centimeter radius has this much volume. We multiply it with this, we get the answer 8 into 10 to the power 11 kg. So very large mass. So you must remember that this density is not very small. It is very high density that the nucleus has. Let's do another example and find the repulsive electric force on proton whose center is at 2.4 femtometer from the center of another proton, and assume that the protons are uniformly charged sphere of positive charge. So let's find out the solution. We consider that the charge is uniformly distributed on a sphere of electrical equivalent to a point and located at the center of the sphere, and hence the force between the two charges is given by the Coulomb formula, E square for charge 1 and charge 2. E square divided by the positively charged divided by 4 pi epsilon naught times r to the power 2. R radius is known to us, and we use this constant, and the charge is 1.6 into 10 to the power minus 19 Coulomb, and that's how we simplify and find out that it is 40 Newton. Now you must remember that this force is not very small, and for the charges, this force is huge force. It is equivalent to 9-pound force, familiar amount of force. However, this is acting on a very small mass. So the huge force acts, and if there is no force to counter it, the nucleus will not get formed. So attractive forces that binds the protons into the nuclei despite such repulsive forces must be greater or equal to this. So we understand now very well that very strong force indeed is needed to counter such repulsive effects. Now let's talk about the spin. Spin and the magnetic moments. Protons and the neutrons, like electrons, are fermions, and they have the spin. And they have the spin quantum numbers. The spin quantum number of half. So each have a spin angular momentum. Spin angular momentum is given by under root s into s plus 1 h cut. More simplifying, we get 3 under root divided by 2 h cut. So the spin magnetic quantum number is plus minus half. Then the spin magnetic moment for the proton and the neutron is given by this E h cut divided by 2 mp. E h cut divided by 2 mp, and the multiplier is different for the proton and for the neutron. Thereby, the potential energy which is created due to this magnetic effect is the magnetic energy which is proportional to the magnetic field, and the constant is this spin magnetic moment. Therefore, the energy is negative when the moment is in the same direction as the B, and it becomes positive when it is opposite to B. So the energy difference is basically from plus to minus, or from minus to plus, and therefore it is 2 times mu times B. So a photon with this energy will be emitted when a proton in an upper state flips and falls to the lower state. So that's how we would like to keep in mind the magnetic moment effect and the spin effect. Let's talk more about it through the nuclear magnetic resonance. And this is what we have now seen applicable, and machines are being made using this technique. So let's first understand this. Suppose we put a sample of some material that contains a nuclei with the spin half in a magnetic field. And when we use magnetic field B, then the spin of the most of them becomes aligned parallel to the magnetic field. And now suppose the electromagnetic radiation at certain frequency to the sample, the nuclei will receive the right amount of energy to flip their spin to the higher state. And once that energy is given, then they will perform the spin flip. And the phenomena is called nuclear magnetic resonance. That is, the nucleons become resonating with the applied magnetic field, and then they perform the spin flip. Now, NMR gives a way to determine the nuclear magnetic moments with the help of experiments. So one of the methods is that the radio frequency radiations are supplied at fixed frequency, and a magnetic field is varied until the energy is absorbed, and the absorbed energy is maximum. So the resonance frequency is found, and it is called Larmor frequency for that value of magnetic field, for which the mass, the magnetic moment can be calculated. The other method is that we use broad spectrum radio frequency pulse and then find out the frequency, which is nu L of the radiative sample. And this will be the same as the excited nuclei will give, returning to the lower state. So again, it is the resonance with the particular frequency through a broad spectrum that this sample will obey, and therefore it will be returning that frequency. In medicine, NMR is basically creating an image method with a higher resolution than the X-rays tomography. In addition, NMR image is safe because radio frequencies are used and X-rays are not used. The radio frequency has little quantum energy to it will not disrupt the chemical bonds, and therefore will not harm the tissues. So what is done is to use non-uniform magnetic field because our bodies are water or the protons to which the NMR is employed. So by changing the direction of the field gradient, an image that shows the proton density in a very thin slice of the body, we can have the image constructed. And the relaxing time can also be mapped, which is very useful to tell what kind of disease that particular part of the body has. Therefore, the nuclear magnetic resonance has become a very fine alternate technique to figure out the hidden images in the soft tissues. X-rays can only detect the things where there are dense materials or hard like bones. But nuclear magnetic resonance technique can be used for the soft, where the body has only water, and the difficulties or the diseases within those parts can be figured out. Stable nuclei. Let's see, A less than 20 are generally containing equal number of protons and neutrons. All the light nuclei are containing equal number of protons and neutrons. All the heavier ones have more neutrons than the protons. So all nuclei with Z greater than 80 and N greater than 126 and A greater than 209 are unstable. You see here the plot is a proton here, number of protons and number of neutrons. I have reversed the figure, but this figure is showing the stability line below, because now the neutrons are more as compared to the protons, and that's how the stability is. But there are radioactive elements that still are really posing problem because they are unstable, for the reason that still they cannot manage, even with the large number of neutrons, the bound state cannot be sustained. Let's see here two examples. One example is boron 10, in which we see the proton distribution. I'm sorry, the neutron is green and the protons are red. So the protons and the neutrons, you can see that the lower level is filled with spin up and spin down proton, spin up and spin down neutron. Similarly, this is filled. Now the top level is with the spin up and the other is spin down. Therefore, this is forming a system in which the overall spin is zero. It is cancelled. And here, boron 11 has this exactly happening, but at the top, there is a spin up and down and one is left. Therefore, spin-wise, the angular momentum-wise, or the magnetic moment-wise, this is posing a problem that the neutrons cannot really, they are neutralized, but the proton has this spin down issue. All the nuclei that have Z greater than 80 and A greater than 209 spontaneously transform their self into lighter ones by emitting alpha particles or beta particles. And the process is radioactivity. So we see here, I've shown here the neutrons and the Z number, and the curve is on the lower side as compared to the Z equal to N curve. And this is unstable. But what is going on is that if alpha decay is happening here, then it is decreased. The alpha, two protons and the two neutrons together are emitted from the nucleus. So Z is decreased by 2. Z is decreased by 2. And similarly, the neutron number is decreased by 2 also when alpha decay is occurring. So in total, 4 is decrease is taking place, and it is coming from here to here. For a negative beta decay, neutron number N is getting decreased by 1, but Z is increased by 1, and therefore it is going towards the stability. Similarly, here the positive beta decay, the Z is decreased by 1, but the neutron is increased by 1. And therefore, it is approaching to this curve, the stability curve. Now, remember that the negative beta decay occurs when the neutron is breaking into a proton and electron within the nucleus. And by doing so, electron gets out of the system and it is a beta particle, and the proton stays inside the nucleus, and therefore you get a neutron decrease by 1 and increase of proton by 1. The positive beta decay is a process in which the proton is decaying, so there is a decrease of proton by 1, and it is decaying into neutron and a positron. Positron gets out of the nucleus, and the neutron increase occurs, and it makes the system stable. There is another process of electron capture in which the electron is absorbed in the nucleus and the proton is transformed into a neutron. And in that case, a proton decrease but increase in the neutron number makes the overall no change at all in the system. The force, that is the strong nuclear force inside the nucleus, was known with certain properties. Yukawa in 1934 said there must be a relationship between the intensity of the force and the mass of the binding particles. So Yukawa went on proposing that the nuclear binding force is transmitted by exchange of some massive charged particles or heavy quanta. So the range of the force is inversely proportional to the mass of the quantum. And the heavy quanta are unstable and they decay through weak interaction. Then Yukawa went on calculating this binding particle that will have the mass about 200 times that of the electron. Later on, 3 particles with the mass approximately 270 times the mass of the electron were found. One was of positive charge, one of negative charge, and one was neutral. And these particles were termed mesons. He said the strong nuclear force between protons and the neutrons was mediated through mesons, now called pions. The discovery of pions occurred in 1947, and that gave Nobel Prize to Yukawa. Yukawa's theory is that every nucleon emits and reabsorbs these pions continuously. There are 3 types of pions: the charged pions, the pi positive, the pi negative, and the neutral pion, pi 0. Since these massive quantas can carry the momentum with them, a proton is going to send a neutral pion to another proton. Thus, the repulsive information will get carried out. A neutron will send a neutral pion to another neutron, and therefore attractive information will be carried out. And a proton is going to send a positive pion, and it will become a neutron. If a nearby neutron is going to absorb it, then that will become a proton. Then that proton can do the same again, will throw away the positive pion, and it will be absorbed by some and will become a neutral. Itself, it will become a neutral. And the other one will become a positive, a proton. As long as the meson exchange is happening, the strong force is able to hold these participating particles together So the nucleons are bound in a system. But the nucleons must be extremely close to each other because these exchanges can occur only in a close vicinity because the pions are massive and they cannot travel far off distances. And that's how the short range of the nuclear force emerged. So determination of the properties or the characteristics of this force is one of the central problems. And much information has come through the scattering experiments, although these scattering experiments can predict certain force laws. The force laws cannot be completely determined from only these experiments. What we know about these nuclear forces is that the force remains same between any two nucleons. Take proton or a proton, take proton or a neutron, take neutron and a neutron, the force remains same. Force is very strong. When particles are close, force is very strong. It drops to zero when they are separated by few femtometer distance. It goes to zero. The potential can roughly be represented by a square well potential. Now, progress has been made, but still we cannot write exact form of the potential, but people have tried. Yukawa proposed that the force, the nuclear force, it results from the exchange of particles between the nucleons, and here we show the nucleon and a nucleus, and we see that the pi meson going out, and here there are two nucleons, and the nucleon is going, and the exchange particle is a meson. In this delta t time, this exchange occurs, and this nucleon absorbs the meson, and this exchange keeps on happening. So Yukawa's proposal for the exchange of the particles between the nucleons gave birth to new idea of interaction between particles rather than force. The exchange is equivalent to the interaction. So particles interact with each other rather than the forcing each other or putting force on each other. If this large force is there, then the virtual pi can become real. Let's briefly talk about this. We will discuss further in detail how these shapes are really found, but you can see a square potential here. The square well is shown. This is between the neutron and proton, or between neutron and neutron. Such a potential is observed when the distance is very short, very small. The potential is very high. The potential becomes positive. That is, a negative potential stands for the attractive force, and the positive potential stands for the repulsive. So the force remains attractive force for certain distances. It is attractive force. Here the potential is negative. It is attractive force. But beyond this position, the force becomes positive, which means that the force, it becomes repulsive. So no further attraction remains between the two nucleons. Beyond this, the nucleons are no more attracted. They remain attracted for these distances, and beyond this, it becomes zero. There is no force at all. So after certain three femtometers, we don't see the force or the effect of the force. Let's talk about the proton and proton. Here we see a repulsive force and then attractive force, negative attractive force, but it becomes repulsive in this, beyond this, and because because the proton and proton has another effect, which is the effect of the Coulomb repulsion. And this part is the Coulomb repulsive part, which becomes dominant, and this force is gone beyond this. It becomes almost negligible, but the net potential is here now telling the story of Coulomb the repulsion. It is a positive potential indicator of the Coulomb repulsion. And here we have the negative. So proton can have the attractive force if they are within the distance of 3 femtometer or small. So after going through these shapes, we have a little bit ideas about the nucleus. We have now seen the force and the radius and how the nucleus is shaped, and we now have the idea of the binding energy. Now we have the idea how the energy is emitted when certain nuclear reaction takes place, and how the instability and radioactivity occurs when the repulsive forces become dominant and the nucleus has to decay. We will continue from this point onward in next lecture. Thank you so much.